Now it's being deployed on the side of buildings, on rooftops, on electricity poles, versus previously it used to be deployed in a pristine central office or a remote terminal. So things like that are changing, and that's creating stress on the semiconductor devices, that's creating stress on the clock, and that's where precision timing comes in.
In this episode of Embedded Insiders, we're joined by Piyush Sevalia, Executive Vice President of Marketing at SiTime, to discuss the evolving landscape of precision timing solutions and the shift from quartz to silicon-based MEMS. Next, Ken is back with another edition of In Case You Missed It, where he updates us on some of the top embedded news stories, and this week we've got news from Shelley Group, Emerson, and Syncos. But first, Ken and I share our opinions on today's modern precision timing solutions.
Hello, engineers, developers, and friends. Welcome to another episode of Embedded Insiders Podcast. So excited to be here. This is Ken Briota, Editor-in-Chief of Embedded Computing Design, and I'm here with Tiara Oliver, our Assistant Managing Editor. Hey, Tiara, how you doing?
I'm good. How are you?
Wonderful. Tiara is did a whole really interesting interview on precision timing and MEMS, and is now going to put me directly on the spot. So enjoy me falling terribly short and then listening to the interview with an actual expert.
Yeah, I thought we would kind of just brief overview of the interview. I thought it was pretty interesting. It was with Piyush Sevalia. He's the Executive Vice President of Marketing at SiTime. And I know precision timing in modern electronic systems is normal, but honestly, I did not know that, this move from analog to digital, that every electronic system or device used a clock. Like
Yeah.
I know like it needs some sort of timing device, but I think when I visualize it in my head, I'm like, why, what is this, I guess?
Well, it's interesting because it's sort of like the synchronization of the timing that's the important part, especially, and it's gotten more and more important as everything's become a little bit more interconnected thanks to the rise and ubiquity of IoT, and now AI and AI at the edge, especially these sort of intersections of um, near real-time simultaneous data processing from data centers to the edge and back via whatever connectivity mechanism. Often it's 5G these days, but sometimes it's wired or whatever, requires really precise timing to make those operations work and be synchronized, and to prevent the dreaded latency and lag time, especially in mission critical applications, things like automotive or energy or security, stuff like that. Timing is really critical infrastructure there.
Yeah, and I think I also didn't realize how, I guess, big this shift of timing was because in our interview, just to overview a little bit, we were just talking about how obviously electronics are advancing, which means these clock systems and precision timing systems have to advance as well. And we were talking about obviously going from quartz to silicon-based MEMS oscillators. And what Piyush was saying was that, quartz has been around for like 70 to 80 years, and we were just advancing so much that now there's a shift over to MEMS. And I'm just like,
Yeah.
using a technology that's been around, or not a technology, I guess, but just
Yeah,
we're using it for so long. So yeah.
the thing that I find interesting is obviously quartz is still being used. Quartz
Mhm.
crystal timing is still out there. And it's still pretty effective too. It's just not at the highest end is where
Mhm.
they're running into the limits of quartz, as I understand it. And that's where MEMS uh technology is really coming into play more often, because it can be more precise, faster, and that kind of thing. Whereas I think quartz is still pretty useful at the if you're not talking about huge AI models or real-time processing or mission critical, high security, low latency stuff, quartz is still fine, I think, generally speaking.
Yeah. Speaking of AI, I was also randomly thinking like everything's moving to AI and edge computing. Will timing eventually matter? I guess timing will, but like, will we need, I guess, a specified system or a unit for it, if that makes sense?
It's interesting. I don't like to make predictions, so I don't
Yeah.
know. But you know, timing is one of the most often used practical applications for quantum computing and like quantum mechanics, because of course satellites and GPS all use precise timing from to maintain orbits and maintain uh GPS accuracy in space. So the I think that that kind of timing is going to become more and more important in these mission critical terrestrial systems as well.
Mhm.
I think it's likely that we have that system in place. It is hyper precise, and the slowest part of it is that uh, you have to transfer back and forth to the satellite in space for GPS. You don't have that problem in terrestrial systems. So MEMS will probably play a part in that, but I think for
Mhm.
the actual timing purposes, it's reasonably likely that we will be using uh, these same kind of clocks that you use to keep GPS satellites orbiting in the proper locations at the proper times all around the world already.
Yeah. I feel like it's probably a good thing we're not pushing AI too much in that, basically.
uh, yeah, the listeners will be well aware that I'm often in favor of not pushing AI too much. So,
Agreed.
Now, here's Piyush Sevalia, Executive Vice President of Marketing at SiTime.
So I came to SiTime in 2008, so it's almost a lifetime ago. It's been 17 years. And before that, I spent a bunch of time at a couple of companies. I've been in the semiconductor industry for about 34 years now. And I started out at Cypress Semiconductor, spent 9 years there, then went to a startup, Econos Communications, helped build it, helped take it public. And then I came here and I helped build this company and take it public too. My role here encompasses all of marketing as well as all of the business units. So in marketing, of course, there is the whole digital marketing outreach. How do we reach out to customers, the public relations, the lead generation, and all that. And then on the businesses, we are organized by three segments and market segments: comms, enterprise, data center, auto, industrial, aerospace, defense, and then mobile IoT consumer. And each of them have a GM, and they all report to me. So my role encompasses everything from lead generation to product roadmaps to running the business, revenue margins, that kind of stuff.
Awesome. That's amazing. So first question, what is the role of precision timing in today's electronic systems? And maybe what are some of the key challenges engineers today are facing when integrating this technology?
Okay. So I'm gonna take us back a few decades.
Mhm.
When the world started moving to digital instead of analog, in the electronics world, when it started moving to digital, pretty much every device needed a clock. The system needed a clock because the whole point of digital, it's all ones and zeros, and there is a reference clock or multiple reference clocks to which these ones and zeros, the data is basically indexed to, so to speak. So everything needs a reference. Now, what's been happening recently, I mean, of course, in the electronics industry, we innovate on performance, we innovate on features, we innovate on reliability, we innovate on a bunch of different things. And generally, the clock speeds have been getting higher because we want to get more performance out of the system and process more data. Generally, the system gets more and more complex. When we started out with a smartphone in the 2007-8 timeframe, you typically had GPS, Bluetooth, and Wi-Fi and cellular as the wireless interfaces. Since then, people have added multiple flavors of Wi-Fi, multiple flavors of Bluetooth, multiple flavors of cellular connectivity. And on top of that, you have NFC, you have in some cases radar. I mean, there's just a whole bunch of wireless technologies being added onto the humble cell phone, so to speak. So the point is that devices are getting more complex. Devices are also getting more dense. The cell phone form factor hasn't changed from the first generation smartphone. Maybe it's an inch bigger or so, but that's about it. But you're packing a lot more electronics into it. And then, of course, you're trying to get a heck of a lot more performance out of it. And what this has done, and there's a fourth aspect to this too, that in general, because of all these electronic complexities, because of how the device is being used, I mean, it's tethered, and I'm using the cell phone as an example. This trend exists in everything else, but how the device is used, it's tethered to a human, and we're on it 5, 6, 7 hours a day. We drop it, we shake it, we do all kinds of stuff to it. We're running with it and all that stuff, right? What we are seeing is that as a macro trend, electronics is just getting much more complex with a lot more electrical interferers coming into play. Electronics is getting subject to a lot more mechanical disturbers, whether it's shock, whether it's vibration, um, temperature changes. I mean, when your cell phone is processing like multiple data streams of high definition video, the processor is going to heat up. That's going to cause a change in the temperature inside. Power supply noise. When you have so much electronics into the device, power supply noise is going to be increased, and that's going to impact the performance. So what we are seeing is that electronic devices, semiconductors, are being subject to a lot more disturbers. I gave you examples of cell phones. You can take an example of cellular radio. Now it's being deployed on the side of buildings, on rooftops, on electricity poles, versus previously it used to be deployed in a pristine central office or a remote terminal. So things like that are changing, and that's creating stress on the semiconductor devices, that's creating stress on the clock, and that's where precision timing comes in. If all these advancements were not there, then maybe the clock did not need to evolve. But now the clock needs to evolve because it needs to be high frequency. It needs to be immune to all of these environmental disturbers and electrical disturbers. And, oh, by the way, the size needs to be smaller because you're just packing so much more electronics in there. And at the same time, it has to maintain its reliability. You can't have equipment crapping out very quickly. So that's what precision timing is. And this is something that we created about a decade ago. When we saw this trend emerging, we said, timing needs to kind of evolve. It's not evolved for the last 80 years. Yes, performance has gotten better, but there needs to be a fundamental shift in the timing devices. And so we created this category called precision timing, and we've been leading the charge ever since. And pretty much all modern electronics, which is subject to the needs of higher performance, more features, higher density, more environmental disturbers on it, will need precision timing.
So I know we're speaking about quartz as a reliable material for these timing applications. Can you explain a little bit more why utilizing quartz-based solutions can be beneficial in these applications, and if you have any examples?
Sure. So quartz has been around since I'd say the 1930s in some kind of volume production. I mean, the usage of quartz really took off in the 50s and 60s with ham radios. It took off when the wristwatch was introduced with a quartz timing device in there. And that's when it took off. And it's basically been the device that electronics industry people have used for the last 70, 80 years. The and it's done really well. I mean, they've performed the material, they've optimized the material to get more reliability. They've optimized the material to get more performance out of it. They've optimized the manufacturing processes to basically get better in terms of yields and manufacturing flow, cost, and all that stuff. So they've done all that. But it's still something that's an 80-year-old technology. And so the question is, how much gas does quartz still have to meet the needs of these new precision timing requirements that the industry is demanding? And that's where our technology, which is silicon MEMS, comes into play. So the fundamental difference between us and quartz is the material. We use silicon, they use quartz. That's one. Second fundamental difference is that we manufacture our devices just like you would manufacture any semiconductor device. And a semiconductor device and the semiconductor industry is one of the most efficient in terms of optimizing the manufacturing flow for better reliability, better long-term life, i.e. reliability, better features, higher performance, and better cost structures. So in that sense, we are leveraging the technology that's been used for the last 30, 40 years, semiconductors, where innovation is just happening at a crazy rate. We are using that to innovate. And we believe that for new markets, for new applications that need precision timing, silicon MEMS is the way to go rather than quartz. I mean, quartz has done really well for the last 80, 90 years. But going forward, it's a new game, and we believe that silicon MEMS is the way to go.
So, as far as performance, reliability, and cost, what makes MEMS better as far as advancements in timing technologies, such as telecommunications and other consumer electronics that you've already mentioned?
Sure. So I'll give you an example. GPS was first introduced into the commercial world back in 92 or 93, something like that. And at that time, the precision of GPS was of the order of tens of meters. Today, the precision of GPS is down to the feet level. And advanced GPS systems can get you precision down to the centimeter level. Now, as the improvements in GPS happen, see, again, GPS digital signal system, it has to rely on a timing device, a timing signal. How that timing signal is going to perform under ideal conditions and then under real life conditions, the worst performance out of the two is going to be the critical path to the performance of the GPS system. And when you have when a GPS is operating, I mean, we've all seen these examples where you're driving a car in a large city with high rises around you, and there's a lot of reflections and things like that happen, and your GPS signal is not as reliable or the precision is not as good. And one of the reasons why this happens, one reason is, of course, the GPS signal is going to be noisy because it's got all these reflections happening. But you could still get better at that if you had a cleaner timing signal. Because the timing signal, the GPS relies on that. And so if you had a cleaner timing signal, you could get better at it. So my point is that in applications such as GPS, in applications such as small cell or radios, 5G radios, in applications such as AI data centers, where optical connectivity is pushing the limits of performance, in all those places, when you start introducing real life conditions, you need better performance from the codes, from the timing device, and that's where SiTime comes into play, and our technology comes into play. So these are just examples. I mean, you'll see examples across all your markets, clearly in aerospace defense. I mean, where these devices are subject to all kinds of shock, vibration, extreme temperatures, all kinds of stuff. Clearly in outdoor deployment of anything, whether it's radios, whether it's base stations, whether it is small cells, whether it's industrial equipment, sensors, deep underground sensors for oil exploration, for example. Uh, those are some of the industrial markets. Robotics, another place where this happens, automated driving. I mean, you have these cameras which are providing intelligence to the car so that level 2, level 3 ADAS can make decisions. That camera signal better be clean. And the computer on the system better be able to react very quickly to it. So data has to be transmitted very quickly there. The signal has to be clean. All this runs on timing. You've got to have a good timing signal for that. And so this is all the places where precision timing helps.
So, kind of looking towards the future, how do you foresee this coexistence or competition between these two technologies? And more so, what is SiTime doing to advance these precision timing technologies and any emerging trends for the future that you're working towards?
Sure. So at the requirements level, we basically see the requirements getting only more stringent. As an example, one of the timing parameters that is very crucial in wireline communications is something called jitter. And I won't go into details of jitter and exactly what it is, but when you go from, say, in optical modules, which are transmitting at 800 gigabits per second, they typically using technology that is 100 gigabits per lane times 8 lanes to give you 800 gigabits per second. When that 100 gigabits per lane protocol moves to 200 gigabits per second, the jitter requirements become half. So clearly, the timing performance from the system has to get better. So that's one trend that we see because it's in service of the macro trend that the overall electronics performance is going to get better. Second, as you get faster in performance, the noise effects have a bigger influence. I was talking to a new college grad from Santa Clara University the other day, and he was telling me about how he's just stepping into the working world. He says, "Yeah, man, this parasitic effects are like a pain to deal with. I mean, we just experience them, and then suddenly your performance gets hit." I'm like, "Yeah, and in analog, parasitics can really mess you up. Even if it's a digital system that's really running really fast, you're going to run into parasitics." That's what I mean by as you get faster, there are all kinds of things that can impact the performance of your system, whether it's noise, whether it's parasitics, whether it is marginal performance of the device, whatever it might be. And so it's imperative to get a timing device that is, as you can say, quote unquote, immune to the effects of these environmental disturbers. So that's another trend that we see. Size is a third trend that we see. You've got to make the devices smaller because electronics is just getting more complex and you're packing more and more in. And you got to do all of this while maintaining the level of reliability. You can't have any early failures and stuff like that because that's just going to screw up the system. So on our end, we have to innovate. We have to innovate as fast as we can. So right now we are on the path to basically cut our jitter in half to meet the requirements of the 200G and 400G per lane optical systems, as an example. Or you have to start operating at lower voltages. I didn't mention power consumption, but that's another factor that comes into play. You obviously want to reduce the power consumption of the system. So cut your power consumption while improving the performance, make the devices smaller, make them more environmentally resilient to the external disturbers. All of these come into play. So on our end, we just have to drive innovation hard. And that's what we do. We're leveraging the power of the semiconductor industry as well as the creativity and the relentlessness of our design teams to just drive innovation. We're just like innovating at, we believe, a much faster rate than anybody else in the timing industry. So these are some of the things that we're doing. Now, recently, what we also did, there's a type of timing device called an oscillator, which puts out a single output signal, clock signal. But as systems get more complicated, you need a timing device that is more integrated, that puts out multiple clock signals. And so in December 2023, we acquired the products from a company called Aura Semiconductor, and they offer something called clocks, various kinds of clocks, buffers, clock generators, network synchronizers, jitter cleaners, things like that. And so now we are offering that. So what we are also doing is we are offering a total system sell, where we are telling the customer, hey, not only do we have oscillators, but we also have clocks. So just come to us. You don't have to go to multiple people to get your devices. And by the way, if you come to us, we'll give you a roadmap to integration where the oscillator and the clock will all be integrated. So expanding our product offerings to cover the various kinds of timing devices is also something else that we have to do. So of course, innovate like crazy, make sure that our reliability and performance is better, make sure, I mean, better meaning improved than from what it is today. We're already better than quartz. We can get it even better, so do that. Make sure that you offer a total system solution that really solves the problem for the customer so that they don't have to worry about it. These are some of the things that we are doing to advance the cause of precision timing. And not just that, but more importantly, solve problems for our customers so that they can rely on us. We become their trusted advisor, and we can just solve it for them so that they don't have to worry about it. If your listeners want to get more information on this, definitely visit our website. There's just a whole ton of information in there, product information, education information, materials, reliability, you name it. We have all that stuff up there. And in fact, we even have an e-commerce section where you can buy samples to try it out for yourself. So visit our website, take a look, see what you got.
Now, here's Ken Briota and this week's In Case You Missed It.
Hello, embedded engineers, developers, and my friends. Welcome to In Case You Missed It, Embedded Insights, the weekly news program all about embedded technologies and solutions from me, Ken Briota, Editor-in-Chief of Embedded Computing Design. And these are our top stories this week from Embedded Computing Design, in case you missed it. First up, Shelly Group has announced that it's now shipping its portfolio of Shelly Wave devices with Z-Wave Long Range. That's ZWLR as an acronym. The expanded lineup is designed to deliver improved range, support for thousands of devices on a single hub, and sub-gigahertz reliability while maintaining simplicity and functionality, the company says. So check that out if you're into Z-Wave and smart home. Our next story comes from Emerson, which has now enabled its Nigel AI Advisor in its flagship test software and the launch of a new edition of its NI System Link software platform. The Nigel AI Advisor is designed to provide engineers with greater proficiency with software tools that address the complexity of test and measurement across industries like semiconductor, transportation, and electronics, the company said. NI System Link is designed to connect test facilities to improve the quality, uptime, and reliability of critical test programs. It does this by allowing engineers to track software revisions, device calibration, and system utilization across various environments, Emerson said. This newest version is specifically designed to simplify setup and installation while maintaining a feature-rich environment tuned to the needs of most labs and test facilities. So check that out when you're doing your next debug and test operations. Finally, we are featuring Synco's MXM GPU computer series, the compact GM1100, which the company says leverages the latest 14th gen Intel Core processors and NVIDIA MXM GPU modules for high-speed edge AI computing and real-time insights. The company says the GM1100 is designed for edge AI applications in vertical industries within transportation and manufacturing in particular. So check that out. Edge AI is, of course, hot, and you need that processing power if you're going to play in that arena. Make sure you look for the In Case You Missed It LinkedIn newsletter every Monday for even more stories that you don't want to miss. You can subscribe over there on LinkedIn, and while you're at it, if a colleague or a friend or a caring loved one sent you this video and you haven't yet
yet subscribed, please do subscribe here on YouTube so that you don't miss any episodes of In Case You Missed It or any of our great programs. Make sure that you are checking out our other programs like Dev Kit Weekly, In Case You Missed It, and Embedded Toolbox, usually every week. Although our show, Dev Kit Weekly, will be taking the month of August off. Visit embeddedcomputing.com for all the news that you need to know in the embedded computing space, published every day. Follow us on LinkedIn and all across the web. And please, reach out if you'd like to advertise on In Case You Missed It, this program, or become a sponsor. That's our show. Make sure you never miss one of our episodes, and I'll see you all real soon.
Thanks for listening to this edition of Embedded Insiders. For more daily news, videos, and podcasts, visit our website at embeddedcomputing.com.